Good evening, everyone. Welcome to today's problem solving section. Yes. So, good evening, everyone. Welcome to today's problem solving section, week 12, course digital VLSI testing. And today's class, we will discuss about the memory testing. So generally, the notations used in this memory testing. So just first, list down some notations. So R is used for the read operation. W is used for the write operation. R0 is used for reading a 0. R1 is used for reading a 1. W0 is used for writing a 0. And W1 for writing a 1. And say if we have a set of memory locations arranged in this way. So if we are accessing this in this order, so we represent with this symbol. And this symbol is for increasing order of the memory address. So here it will be having multiple cells. Again, if you are accessing in this order, if you are accessing in this order, so this is the symbol used. The circle I'm just drawing for representing. There is no circle. It is for the decreasing memory address order. So further we have one more symbol like this, which is for either increasing or decreasing address order. So with this, now we have a symbol like this. This is to write a 1 to a cell containing 0, or the cell has a rising transition. This represents write a 0 to a cell containing 1, or the cell has a falling transition. And this symbol indicates that the complement, we have to means the cell is, the content of the cell is complemented. And this indicates write a 0 to a cell containing a 0, and a smaller arrow represents writing a 1 to a cell which is already containing 1. Okay. With this notations, next we will see the memory faults. The sufficient fault, like structured fault, TF, which is for transition fault, CF, which is for coupling fault, NPSF, which is for the neighborhood pattern sensitive fault, so one by one we will discuss each of the fault type. So to briefly discuss using some state transition diagram. So let's consider for instance stepwise and transition. So to begin, state transition diagram. So this represents the behavior. We will show the behavior of the behavior of the cell. So for the good cell, so if we consider that uh, initially 0 is written represented by S0, initially 1 is written to the cell represented by S1. So now if we are writing a 0, it will remain in this state, and if we are writing a 1, it will remain in this state. This transition will occur if we are writing 1 to a cell, and this transition will occur if we are writing a 0 to the cell. Now let us consider that the cell has a stuck at 0 fault. So only possible state is 0. So when we write a 0, it will remain in the 0 state, which is same as the good cell. Now when we write a 1, then also it will remain in the same state because of the stuck at 0 fault. Now similarly, if we consider that we have a stuck at 1 fault and S1. So now as before, if we write 1, it will be remaining in one state. And now if we write 0 also, it will remain in the one state because of the fault. Now let's consider another fault type, which is transition fault. So represented by TF. So any rising transition, but still it remains in the 0 state. So we have S0 S1 state. Transition is from 0 to 1. So this transition is now removed. Instead of that, a 0 to 1 transition, that is when we write the 1, it remains in 0 state, and 0, it will remain in 0. This transition is as it is, unaffected. 1 to 0 is unaffected, and when we write the 1. So this is the transition diagram, a state diagram, transition diagram, when we have a transition. Further, let's see what are the fault types. We have SAF fault, which we have already seen, which is a stuck at fault, and now this is for the memory. Next we have transition fault, that is fault makes a transition. So say this is making a transition, that is say from 0 to 1 transition, but the cell remains in 0 or 1, that comes in this transition fault. Now coupling fault, that is change in I causes unwanted change in J. Next is inverse coupling fault. CFIN. This is any up or down transition in J causes change in I. Here, if we say I and j, that means we have two bits. Like previously we said one state, so S0 or S1. Now we have Sij. So total four different states. Uh, Further fault, we have independent coupling fault presented by CFID. This presents like any up or down transition in J holds I 0 or 1. If there is an up transition in J, it holds the I to 0. If there is a down transition in J, it holds the I to 1. Next is we have dynamic coupling fault, which represents between cells in different world. And also further we have bridging faults short between more than one cell. And next we have state coupling fault, which is represented by SCS. Now let's see if we have the two uh, bit, say Sij. Let's see the state diagram for that. So now we have two bits. So we will be having four different values. S00, S01, S10, S1. Now, if we write both I and j is 0, it will be in this state. So W0 for I and W0 for j. If we write a 1 to the j, we will go to this state. So W1 for j. And if j is 0, again in this state. And to come to this state, we have to write a 0 in I and a 1 in j. And to come to this step, it's W0 I W1 I. And to be in this state, both I and j needs to be 1. To come to this state, j should be 1. To come to this state, j should be 1. Now for this, to remain in this state, W1 for I, W0 for j. And to go to this, W0 should be I, W1 should be I. So this is considering two step. Yes, I. So now again, let's consider a coupling for inverse coupling. So this is represented as CFIM, and any transition inverts the contents of the same. So let's first draw which and all transitions will remain the same. And at the end, we will draw the transition which are occurring like new. So this transition says W0 for I and W0 for J. This transition for W0 for I, W1 for J. And this transition W1 for I, W0 for J. This one W1 for I, W1 for J. And this transitions will also remain the same. Now what do we have to write? 1 for I, then 0 for I. This transitions will also remain same. 0 for I and 1 for I. This will also remain same. 0 for J. And this one 0 for J. Now instead of going here from S00 to S01, content of the cell should be inverse. It will go to 1 1 when we write up 1 to J. And similarly, content of the cell will be reverse when we write the 1 to J. I hope this is clear. Next, we will see another symbol of the state diagram. For another type of state of transform, which is say this transition, we proceed to the remaining one, which is CFI in the context one. So again, we will have S00, S01, S1, S1. So, like before, first we will draw all the transitions which are same as the fault 3. 0 for I, 0 for J, for I, 1 for J, 1 for I, 1 for J, and this two transition will remain same. 1 for I, W0 for I, and this transition will also remain same. W0 for J, because we have one fault from 0 to 1, one distance. And this fault, this transition will also remain same. And this one, W0 for I, W1 for I, W0 for J. Here also we have the transitions. W0 for J, W1 for J. Now, when we write the 1, that is 0 to 1 transition, content of 0 should go to 1 1 This fault, any change in the J, transition in J is affecting the I. Okay. Further, next we will see for the memory test. We use March test algorithm. And one such March test algorithm is say maths, which consists of sequence of March elements. In this consist we can write a 0 in any order, and also reading is any order. So read 0, then we have to write a 1. Next, this 1 has to be read. So this is called maths. Now next algorithm, this will consist of addition of some more elements to this with certain, like now let's specify this to be in this order of reading the 0. Next, specifying the order to read it 1 in this order and writing a 0. So in this way we have different algorithms. Maths plus plus, which consists of this first writing in any order because it's the first time. So next we specify the order that we read in this order, write the 1 in this order. In this order we read a 1, write a 0, and then we have written a 0, so let's read that. So in this again we have March C minus, March X, March C minus, March A, March Y, March B, other algorithms. Let's just see some examples. Say we are performing the memory test using maths plus algorithm. So let's consider this 3 cross 3 array. So this is the good machine. So after we write 0 to the machine, so say consider like first we write a 0. Next say we perform the read 0. After this we have to perform the read 1 and then read 1. Further, maths algorithm says we have to write a 0. Okay, so now let's consider a fault in the cell 2 comma 1 is restricted to 0. So when we are writing a 0, it will be all 0. No problem. When we read a 0, so there is no problem. Now we are writing as so this cells will not have any problem. This is the cell which is 2 comma 1. So it remains in the 0 state. So we can identify this fault when we are reading the 1. Next, again, we have to write 0. So in this way, the fault in 2 comma 1 cell stuck at 0 can be identified when we are reading the 1. So again, we will see one more example. So I'll just add one more slide. So before we saw for stuck at 0, let's again draw the machine. So we are first writing 0. Again, same 3 cross 3 cell. And then we are reading the 0. Further, we are writing a one. Okay, so here, this is a good question. And then we will read a one. And we will write this. So this is the procedure of the mass algorithm and this is how it will be when there is no fault. The memory content. Next, let's consider a fault in the cell 2, 1, which is stuck at 1. So first operation is to write a 0. The content of this cells, there is no problem. But the 2, 1 will be 1. So we can identify this when we are writing 0. Because it's a stuck at 1. And next, writing 1, yes, no problem. Further, we have to write a 0. So this content of the cells remain the same, but this bit remains. With this, we will solve some of the previous year questions. So I will wait for some 2 minutes. So we can observe that here we are able to detect the form, and similarly here we are able to detect the form. Sorry. Yeah. So now next first question: which type of RAM supports the refresh technology? So if we consider a DRAM, we have a capacitor. Say we have some access transistors which is connecting to bit line, word line. So let's consider we are writing a one to this side. So that means it will come here, it will come to this capacitor. Now this capacitor has to charge to one. So the content of the memory is stored in the capacitor. Now this one is stored, it's a capacitor. So there is leakage. That means the charge in the capacitor starts to leak. So we need some refresh circuitry. So this, say at this point we start to refresh. So we need some refresh circuit. The DRAM cells use the refresh circuitry. So that it sees this one, it is seeing that it is leaking away. So this one, it is again charging to VDD. And if it sees a 0, it will meet in ground state. So option A is the correct answer. Next question. If we try to read from a SRAM cell having stuck open fault, what will be the value at the output? So if we consider an SRAM cell, it consists of a back-to-back inverter with the two transistors. This is the 60 SRAM cell. where this is connected to some bit line, word line, bar between words. So now, if this is open, that means this is access. So previously, if say we read a 0, so it is open. So this transistor, this RAM cell will get that value, or if it is 1, it will get that value. So whatever is the previously read value will be within this as RAM cell. The correct answer is previously read value. So next question. A coupled cell is enforced to value 1 when the coupling cell has a transition from 1 to 0. Identify the type of coupling. So if we have a state coupling fault, the coupled victim cell is forced to either 0 or 1 if the coupling aggressor cell is given is in a given state. What is transition coupling, inversion coupling? A transition in the coupling cell complements the content of the or inverts the coupled cell. And what is the independent field? Coupled cell is forced to be 0 or 1. So if 1 is the value is given in the question is value 1. So if the coupling cell transits from 1 to 0. Okay, whereas if it was given that value is 0, so it coupling cell transits from 0 to 1. So it's option C. So it's not the state coupling fault or inversion coupling fault. That is, if we write a 1 to the cell and there is a transition from 1 to 0. It's option C is the correct answer. Next question. 0-1 algorithm scans the memory cells. Option A, from one end to the other end with alternating zeros and ones. Option B, from one end to the other end with alternating zero with all zeros and ones, all ones. And next is randomly with alternate 0 or randomly with all 0. So if we see, it's like all zeros, all ones. So it's like writing first all zeros and then all ones. It's like either all zeros or all one. And it's not the alternating, neither the randomly. It's like all 0, all 1. Option B is a correct answer. Next question, which of the following algorithm has a non-linear time complexity? So if you see the time complexity of the 1 algorithm, it is 4n. And for the checkerboard algorithm, it is 4n again. And for GALPAT, GALPAT algorithm, it is 4n square. So you can see this for this algorithm. It is the quadratic type, so it's a non-linear type. So right answer is option C. Which of the following is capable of detecting transition faults? So if we see, this is the content from this taken from the slides, NPTEL slides. So if we consider the max plus algorithm, it is given that it also detects all the array decoder faults, static fault, and the transition faults. It also detects the transition faults. So it's max plus plus. The next question. Which of the following March test is considered to be redundant test? So if we see the content from the slides for marching 1 and 0, it is given that it, however, is a redundant test because only the first 3 march elements are necessary. So it's writing R0, W1, R1, R1, W1, R0. So it's like only these three elements are needed, and the other elements seems to be like redundant. Maybe the order of the addressing may little change, but that's why it is called as a redundant list. So it's marching 0 and 1. So next question, which of the following march tests can deduct stuck open faults? Open fault is, if you see march C, it removes the redundancy in the march C and it deducts AF, SAF, TF and all CF. It's not deducting SOF. But if we see the extended march C, it covers the SOF in addition to the above mentioned faults. So extended march. Next question, which of the following algorithm is mainly used for characterization because it can cover a large number of faults? So it's given which of the algorithm is used mainly for characterization. So if we see this algorithm, Galpet, which is the galloping pattern, Galpet, its complexity is 4n square, which is huge, and it's given that it's used only for characterization. This is the algorithm. Let's read further. A strong test for most of the faults. So it is the test which covers all of the array fault, transition fault, coupling fault, stucket faults. And like this, all of the faults are detected. So it's used for characterization. Next is data retention faults are detected. So how to detect data retention fault? Now what are data retention faults? They are refresh circuitry has a fault. That means RAM solution 1, it's this because of the leakage, it's sorry, because of the leakage it is trying to discharge. Sorry. So because of the leakage, uh, it's like we have one. There is a the refresh circuitry. If it sees there is a discharge, like periodically it will bring it back to one. So this is the work of the refresh circuitry. So, but if there is any fault in the refresh circuitry, the cell value will be from 1, it will be discharged completely to 0. Now, either there can be a leakage fault. Now, SRAM doesn't have any refresh circuitry. So, the one fault can be the leakage fault where the static data loss, that is, there is some defect in the pull-up transistor. So, it's like back-to-back. Sorry. I think I have done some mistake. Sorry. It's not a diode, it's an inverter. So this back-to-back transistor, so there may be a pull-up and a pull-down transistor. So if there is some fault in this pull-up transistor, That's why it's not properly pulling up to 1. So there is some leakage. So that can be one of the faults. So now how can we detect this? We read at this point. We see it's 1. We read at this point. We see again it's 1. We see some discharge, but maybe because of noise smudging, we read as 1. But at this point, we see it's a 0. So we read here and we are able to detect this fault. This is like successive read. So successive read operation. Sorry. Memory testing. So memory is consists of a regular arrangement of the cells and it consists of a specific architecture. It consists of like components like sense amplifier, decoder. Decoder can be say row decoder, column decoder, and this architecture can consist of a bit accessible memory or a word accessible memory. Now let's see one by one. Wafer, we have a wafer. Now we perform the full probe test. Why in a wafer we want a probe testing means this is a wafer. We have a die. Now this die, if we perform packaging, we will have external pins which we can connect to the ATA and pass the test patterns. Apply the test patterns. But when we have a wafer, we don't have any pins. So we use probes to test it. Next we use laser repair. See, we have two lines. A short between the line because of some material. This short can be removed by the laser. So this laser repair is performed. Then packaging is done. Pre-burn-in test means we apply some patterns like pattern of all zeros, pattern of all one. Our packaging is done, so we have the pins. Next, we do the burn-in test where we stress the system and perform the testing. Next, post-burn-in test and marking, then the final testing. Then which visual inspections and QA sample test. Finally, the chips which pass the test are shipped. Next, offline testing of RAM. So it can be a parametric test of AC and DC, reliability screening, long cycle testing, burn-in, either static or dynamic burn-in. Functional test, which includes the device characterization, failure analysis. Fault modeling means any, say we have a particular defect. This defect is modeled using the fault models. And they're simple but effective, accurate, and realistic. Test algorithm generation, small number of test patterns, data background, which should give high fault coverage and short test time. So DRAM, we have an address. So we have both column and row decoder. Now in a memory cell, say we select a particular memory bit cell. The content of the cell is read using a sense amplifier for reading. Why we need a sense amplifier? Say we have bit and bitline bar. Say this is the bit line and the other one is a bitline bar. So here the voltage is when the sense amplifier goes to say V plus delta V. We can't say V plus delta V, just a plus delta V. And say this potential changes to V minus delta V. In the sense amplifier, we observe that if at least not this. The sense amplifier can say that okay, because there is a delta V increase, so this is a VDD. So now before we have to charge the node to 1 so that it can be written as 1, but now a delta V change is enough to say whether it is 1 or 0. And we need refresh circuitry because and refresh logic because it's the storage is in capacitor, so it will leak and we need to periodically refresh it. Now say if we have a data, input data, this is going inside data register, and now we are writing it. Say this particular cell we want to write. So we will use write drivers to write the content. And whatever whether we are doing read or write, which can be selected is in the chip heading. So this is the DRAM functional model example. So it consists of D and Q lines and the address lines and the memory cell, the memory array, and other column decoder, row decoder. Okay. So next, functional fault model. So the classical fault models are not sufficient to represent all the important failure models in RAM. Sequential ATPG is not possible for RAM. Functional fault models are commonly used for memories. They define functional behavior of the faulty memory. What is this sequential ATPG? Can we consider all of the memory cells as a flip-flop and use the sequential ATPG, which is also not possible when it is little huge. And new fault models are being, it will become huge complex, are being proposed to cover new defects and failure in modern memories, new process technologies, new devices. Static SRAM models, stacked fault, which is we already seen, or line SA0, SA1. A stacked fault SAF occurs when the value of a cell in a line is always 0 or stuck at 0, the fault, or always 1, stuck at 1 fault. A test that detects all SAFs guarantees that from each cell a 0 and a 1 must be read. Transition fault. Cell fails to transit from 0 to 1 or 1 to 0 in specified time period. A cell has a transition fault if it fails to transit from 0 to 1 or 1 to 0. That means with this fault model, the stuck fault model, every cell, if it does not have a stuck fault, we should be able to write a 0, read a 0, write a 1, read a 1. And if the cell does not have any transition faults, we should be able to make any cell perform transition from 0 to 1. Like any content which is 0, we should be able to write 1. Any content of the cell which is 1, we should be able to write 0 to the cell. And say an example. What is this? An example for say A, it is having a transition when it is having a transition from 1 to 0. This means 1 to 0. It remains in 1. So this is a transition fault. Static RAM fault models or array decoder fault. Address decoder fault. Address decoder fault AF is a functional fault in the address decoder that results in one of the 4 kinds of abnormal behavior. Say we have an array. For now, let's consider 2 cross 2. Given a cell address, no cell is accessed. Say now I am giving 2 comma 1 as the address, which is for this. Let's consider that. And this is 1 comma 1. No cell is accessed. So for this, no cell is accessed. So we have this AF fault. Next, when a certain cell is never accessed by any address, given a certain address, so we have this particular cell. If we give any of the 4 address, we are not able to access this. Then also we have an address decoder fault. Next, given a certain address, multiple cells are accessed. Say we are giving an address to be 2 comma 1 and it is accessing this cell and it's accessing this cell. So again we have an address decoder fault. Next, a certain cell can be accessed by multiple address. Now see this is the cell. which can be accessed with 1, 1, 2, 2. So multiple address we can access this cell. So that's again another type of address decoder fault. RAM fault models CF coupling fault. A coupling fault CF between two cells occurs when the logic value of a cell is influenced by the intent of or operation on another cell. Coupling fault, state coupling fault, CFST, state coupling fault. Coupled victim cell is forced to 0 or 1 in a coupling aggressor cell is in given state. Inversion coupling fault CFIN transition in coupling cell complements or inverts the coupled cell. Next is independent coupling fault, which we have already seen. Coupled cell is forced to 0 or 1 if the coupling cell transits from 0 to 1 or 1 to 0. When it is 0, it, another cell transits from 0 to 1 and 1 when it is 1 to 0. So in intravert coupling means this cell content is affecting this cell. So it's intravert coupling. And interword coupling means this is a different word and this is a different word. So this is between the word and this is within the same word. Next type of fault is for the RAM fault model is the disturb fault. The victim cell forced to 0 or 1 if we successively read or write aggressive cells may be the same cell. So this hammer test. Next is read disturb fault. That is, there is a read disturb fault if the cell value will flip when being read successively. Next type of fault is the data retention fault, which occurs because the DRAM circuit we need refresh. So if refresh circuit is not working, or there is some leakage fault. In the SRAM, there is a leakage fault or static because there is static data loss, maybe because of the defective pull-up network. Now time complexity. If we have an n as the time complexity of our testing algorithm, and if we have a memory of 16 GB, it takes 2.8 minutes. So this is considerable time. But when we have n square, it takes almost 915 centuries. So one algorithm we saw which has a time complexity of 4n square. Now if it is n power 1.5, it takes 255 days. Now if you see the memory size is also increasing. So with this, the test time will increase. So we prefer the time complexity is n. Next, RAM test algorithm. A test algorithm or a simply test is a finite sequence of test elements. A test element contains a number of memory operations, access commands, data patterns, background specified for read and write operation, address sequence specified for read and write operation. A March test algorithm is a finite sequence of March elements. Now, what is March elements? We have say read 0 and specific order of write 0, specific order of reading 0, and say another specific order of write 1, read 1. So this things, this each, if I just say this is one element. So these are the March elements. So I can also have read 0, write 1. This is another element. So like this, these are called March elements, and we need to specify like which order of address we have to access, whether it's a read or write, and whether it is a 0 or 1. So March element is specified by address order and a finite number of read write. The next is March test notation. So we have seen this notation. This address sequence is for ascending order. Address changes in this descending order, and this symbol represents address sequence is either increasing or decreasing, that is ascending or decreasing in descending order. R for read operation, reading an expected 0 from a cell R0, reading an expected 1 from a cell R1, and W for write operation, writing a 0 into a cell W0, writing a 1 from a cell W1. Now if we consider this maths plus algorithm, which is a March algorithm, so any sequence we have to write a 0, and in this order write a 1, in this order write a 1, read a 1 and write a 0. So it's like any sequence write a 0, then in the ascending order read 0, write 1, in the descending order read 1, write 0. Next is RAM test algorithm. A test algorithm or a simply test is a finite sequence of test elements. I think these are good. Classical test algorithm, M-scan. So 0-1 algorithm, also known as M-scan. SAF is detected if the address decoder is correct. Not all address decoder faults are covered. So a test that detects all AFs, it contains a match elements, writing on content, say either 0 or 1, it's complement of this and the normal. And the normal is initialized to the proper value before each match element. So we have a solid background pattern and the complexity is 4 in. This is the sequence, match element. Let's write in this order. We first write a 0. And then in this order we read a 0. In this order we write a 1. And in this order we read a 1. Next, classical test algorithms, checkerboard. So checkerboard algorithm, 0-1 algorithm with checkerboard pattern. So it's again the complexity is 4. Must create true physical checkerboard, not the logical checkerboard. So it detects all the it is for SEF, DRF, that is data retention fault, shorts between cells and half of the transition. Not good for address decoder fault and some of the coupling fault cannot be good. So next is the classical test algorithm, this galloping pattern, complexity is 4 and square. Only for it's used only for characterization and it's a strong test for all faults. It detects all the array decoder, transition fault, coupling fault, stuck faults. All of these faults are getting detected. So it's like write the 0 to the background. So BC is the base cell and OC is the other cells. So for the base cell equal to 0 to n minus 1, complement the base cell. Other for OC is equal to 0 to n minus 1, OC not equal to BC. Read the BC and read the OC. So write the background one, step into this step 2. Similar to this, we have another algorithm, classical test algorithm, walking pattern. This algorithm is similar to GASPAT, except that BC is read only after other cells are read. So we reduce the complexity. Now the complexity is 2n squared. Simple March test, 0-1 M-scan, algorithm modified test sequence, MATS, or type address decoder false. So, and next is handling. What is this? If we have an address, and there are two cells, and an OR gate. This can be OR or AND gate based on the fault. So this is the OR type. So OR type to detect we need to write a 0 for AND start with write 1. Next we have written so read 0 and write 1. So next is next is maths plus So it's for both unmet ornate fault, arithmetic fault, and static fault. So the suggested sequence for unlinked static faults is this. Next is marching 1 and 0. So marching 1 and 0, marching 1 is beginning the writing of a diagram of zeros, then read and write back implement values. And read again to n. So for all the cells from 0 to 1 minus 1, and then from cell minus 1 to 0 in 7 and time. Marching 0 follows the exactly same pattern with the data reverse. For AF, SAF, and TF, but not all, but found of coupling fault. So it is complete test, that is all faults that should be detected are covered. It, however, is a redundant test because only the first three March elements are necessary. So you will find some elements which are like redundant. So this element is redundant. This is redundant. So if you see like this elements seems to be redundant. Maybe this order of address access is little different, but still the patterns are redundant. March test maths plus plus also for AF, SAF, TF. So optimize marching 1-0 scheme, and it's completely redundant. Similar to maths plus but allows for coverage of TFs. The suggested is like this order. You can see we have specified the order for redundant. March X called marches because the test has used one without being published, so it detects array decoder fault, circuit fault, transition fault, and inverse coupling fault. Whereas March C is having all the coupling fault, but its semi-optimal has it consists of some redundant patterns. Next is March C minus. So we remove the redundant March C elements. Also that it can detect all the fault, but it's optimal as it is irredundant. Next is extended March C minus, which covers the step open fault in addition to the above faults. And this is the marching pattern. So this is the summary of the fault detection and for various March algorithm with its March sequence. And here is a comparison of the March test. So you can see these are different types of coupling fault, stuck open fault. These are covered by different March test. Next is the word-oriented memory. A word-oriented memory has a read or write operation that accesses the memory cell array by a word instead of a bit. Word-oriented memories can be tested by applying a bit-oriented test algorithm repeatedly with a set of different data backgrounds. The repeating procedure multiplies the testing time. So if we are repeating say 2 times and we have a test time of say t, now 2t will be the test time. Testing word-oriented memory. So till now, if we consider a bit and the background was a bit, now when we are going for the testing the word-oriented RAM, so the background bit is now replaced by a background word. So the maths plus plus, if we see, it's a background word writing the background word. So conventional method is to use log m plus 1 different background for m bit word. So called the standard backgrounds, if we consider m is equal to 8, it's all 8 zeros or 0101 8 for 8 bits, 0011 or 4041. And apply the test algorithm log m plus 1, that is 4 times. So the complexity is given as 4 into 6n by 8, which is 3 times n, where b is the complement of the a. Next is the cocktail march algorithm. So the motivation, repeating the same algorithm for all the log m plus 1 backgrounds is redundant so far as the intra-word coupling faults are concerned. Different algorithms target different faults. So the approach is that use the multiple background in a single algorithm run. So we merge and forge different algorithms and backgrounds into a single algorithm. So for a good for word-oriented memory. Memory March CW. So algorithm March C minus for the solid background, all zeros. Then a 5 and March for each of the other standard background. Sorry. So the other backgrounds include 0101 or 2011, 0011, and this is the March pattern. So the result complement complexity is 10 plus 5 log mn, where m is the word length and n is the word count. Time this time is reduced by 39% if m is equal to 4 as compared to with the extended March C minus. So improvement increases as m is increasing. So I will wait here for a few minutes, then we will continue. So here we saw some of the variation of the March algorithm for the word-oriented memory. So next we'll see multi-port memory fault models. So the cell faults, single cell faults which are SAF, stucker, transition, data retention fault. So two cell coupling faults are inversion coupling fault, state coupling fault, independent coupling fault, CFIM, CFST, CFID. So the port fault, stuck open fault, which is SOF, address decoder fault, AF, and the multi-port fault, which is MPF. Now, if we consider that there is a interport between the word length short. That means here there is a short. And again here there is a short if we have an interport bit length short. So we have an interport WL word length short and an interport bit line short. So these are the bit lines and these are the word lines. So interport word line short means this there is a short. This is for interport in the faulty circuit. Next, for the interport bit line short, this bit there is a short, this bit you can see there is a short. So the functional test complexity is big O n square. Next is why memory fault simulation. Fault coverage evaluation can be done efficiently, especially when the number of fault models is large. In addition to bit-oriented memories, word-oriented memories can be simulated easily, even with multiple backgrounds. Test algorithm design and optimization can be done in much easier way. Detection of test algorithm on unexpected faults can be discovered. Fault dictionary can be constructed for easy diagnosis. So the sequential memory fault simulation, the complexity is n cube for two cell coupling fault. For each fault, n square for two cell coupling fault. So fault inject, we first inject the fault, then for each test element, n for March, we apply the test element and report the error output. So in the parallel fault simulation, in this simulation, each of the fault model has a fault descriptor. The descriptor consists of AGR, which is for aggressor, SPT, which is for suspect, VTM, which is for victim marking, RCV, which is for recover, and CFST is you can see CFST we have seen somewhere that okay sorry. Yeah, it's from the coupling to circuit fault. So this asterisk represents all other cells are suspect, and this at the rate, which is a single cell fault, that is for the same cell. So next, this algorithm has a complexity of n square. So for each test operation, if the output is aggressor, then mark victim cell. If output OP is recover, then release the victim cell. If OP is victim, then report the error. So this algorithm is like for each of operation, we set the flag values for the aggressor based on the flag. For each victim cell, we set the victim cell aggressor address. And if the OP is equal to RC, we recover. We clear the victim and aggressor. If it is a victim, then we mark detected. So same thing which we have given here. It's written in this algorithm. So the coverage of March test. So extended March C minus has 100% coverage of stuck open fault. Test algorithm generation rules. Given a set of target faults, generate a test with 100% fault coverage. Given a set of faults, models and a test length constraint, generate a test with the highest fault coverage. Priority setting for fault models, test length or test time can be reduced. Diagnostic test generation need longer tests to distinguish faults. So the test algorithm generation by simulation, we have a March template from the abstraction. Like first we have, I just highlight it. So if we see, first we mentioned this read 0, 1 values. Like what are the values which you want to read it. So next we remove them and we come to the next abstraction level. In this abstraction level, we specify the address in which order we are accessing. In the next, we can see that we have obtained the template. So from any March sequence, we are removing the 1 and 0, just keeping the write and read, and removing the order of the address. And finally, we have obtained the template. So next is the test. The template set. Exhaustive generation, the complexity is very high. That is like if we exhaustively generate like these templates, for n equal to 9, we will get around 6.7 million templates. So the heuristic should be developed to select the useful templates. Now, what is useful templates? This also we will discuss. So, for example, a template is generated with a read at the end. So, will this be okay? Read at the end is fine. A template is generated with an ending with like at the last we write something. So without reading this will not be useful. So this templates can be removed, and say we have a successive write operations or successive read. So this we will see what are useful templates. So next is tax procedure. Initialize test length as 1 by n. T1n is equal to W. So increase the test length by 1n, apply the test generation operation. So next is the filter operation. Apply the filter operation. Assign address order and data backgrounds. Fault simulation using this algorithm and drop the ineffective test. So repeat the step 2 to 6 using the new template and see until constraints are met. So template generation and filtering. So to generate the generation heuristic from a shorter template T. So our insertion everywhere in T except in the beginning. So at the first we like for example, I insert a read 0 here in a memory cell, but here I have not performed any write. So will this be useful? This will not have any meaning. Like I have not written, we don't know what is the content of the memory cell. We have not written anything. But at the beginning, we are starting with the reading operation. That's why inserting R anywhere is fine, but except in the beginning. Next, R here. So expansion in a template element, insert R at the beginning or end, anywhere in the template element. W insertion expansion. So you can see here. Then filtering heuristic. So we have a consecutive R. This is not like I have written a 0, reading 0, reading 0. This consecutive reading can be filtered. That is the repeated R or trailing single write. Say we have some operation read 0, write 1. We should begin with the write. So write 0, read 0, again read 1. So I write a 0. So trailing with this write operation without a read is also can be filtered out. So tags example, target fault models, SAF, TF, AF, SOF, and other coupling faults. The timing constraints, infinite. So these are the March patterns for different with their respective time complexity. So this is the different testing and its respective fault coverage. Now if you see SAF fault, so this represents the SAF fault coverage by this particular algorithm. And M11, if you see, it's just a write operation without any read operation. So its fault coverage is like 0. Okay. So what can BIST do? What are the functional faults to be covered? Static, dynamic, operation modes. What are the defects to be covered? Open, short, timing parameters, voltage, and current. So, can it support fault location and redundancy refill? Can it support the burn-in? Can it support on-chip redundancy analysis and repair? Does it allow characterization test as well as mass production test? Can it really replace ATE or the laser liquid machines? Programmability, speed, timing, accuracy, threshold range, parallelism. So typical RAM-based approaches, the methodology includes the processor-based BIST, programmable with or hard-wired BIST, fast and compact, or the hybrid version. So interface, serial interface, if we have, then we can use the scan, which we have already seen 1149.1 architecture, or parallel, embedded control or hierarchical, and patterns or address sequence, March and March like, and pseudo-random others. So typical RAM-based architecture, so we generate the pattern, say we apply the pattern to the RAM cell, and the responses we obtain, and which is compared with this, and we give whether it's a go or no go, whether it's a faulty or fault free. So, and we have a control circuit. EDU RAM BIST example. So again, we have a memory cell, RAM memory cell with, this is the complete RAM architecture that we have seen with the row decoder, column decoder, QD, but added with that, we have a memory BIST which is applying the record patterns. So DRAM page mode read and write, so you can observe that wherever this is 0, we have the Q. The BIST architecture, you can see here, it's a detailed BIST architecture. So now the concluding remarks, BIST is considered the best solution for testing embedded memories, low cost, effective and efficient. Further improvement can be expected to extend the scope of the RAM BIST, timing or delay faults and disturb faults, BISD and BISR, CAM BIST and flash BIST, BIST, BISD, BISR compiler, wafer level burn in and test, good, known, good, die. Okay. So with this state diagrams, we have explained of the few fault types. And what is the march sequence? And we have solved like how we are able to detect, say, a circuit fault using this march sequence. And we have solved some of the previous year questions. So with this, I will end today's section. Thank you so much.